All right, this is Mrs. Crary, and this is our lecture on motion diagrams. A motion diagram is a representation of a moving object at successive time intervals. So we're going to also include some velocity vectors and some acceleration vectors at each position. Here's a key. The time interval between the adjacent positions in the motion diagram are equal to one another. Okay, so I want you to think about a car that has a leak. He's got a leak. You're driving down the road at a constant speed, and he's got a drip on the ground that is going to have equal distance between the drips because he's going at a constant speed. If he started to accelerate, all of a sudden the drips get farther and farther apart. If he starts to slow down, the drips get closer and closer and closer. So a motion diagram lets us kind of start to figure out what's happening with the velocity, acceleration, and the position of the object. So let's take a look at this situation here. Let's look at picture A, which I have started pointing at it in red. It's the red vectors represent the velocity, and then violet, they call it, is going to represent the acceleration. So let's draw a dot for each location of this car in picture A. So I have this dot, and I want you to notice that the distance between each one of those dots is the same. And again, what do we know about the time intervals? The time intervals are equal between the dots, and that was the key point. So if the dot distance between the two are the same, the delta x over delta t is the same. And so this velocity vector, which is shown here in red, the length of the velocity vector represents the magnitude of the velocity vector. So for example, if I were to have a velocity vector here and a little teeny velocity vector there, the longer the velocity vector, the larger the magnitude of the velocity is, okay? So now let's look at A again. Is there any change in velocity between the dots? No, and therefore the length of velocity vectors are the same. If there is no change in velocity, what is my acceleration? 0. Therefore, you don't see an acceleration vector because the acceleration is 0. Now let's look at B, and let's draw some dots like our oil leak on the ground. So I have a dot here, he has a dot here, and then all of a sudden the distance between those dots is becoming larger. But remember, the time between the dots is the same. So that is the key. This time intervals between the successive dots are the same. Okay, so I have a velocity vector. It's moving to the right because the car is moving to the right. But notice the length of the velocity vector is getting larger, which indicates that the velocity is getting larger. And what direction is the velocity? The velocity is positive. Do I have acceleration in the situation? Yes, I do. Why do I know I have acceleration? Because there's a change in velocity. And which direction is the acceleration? It's positive. And therefore the car is speeding up. That's why I have this larger distance between successive dots. Let's see if Mrs. Crary can pronounce. Okay, so now let's take a look at C. So I can have a dot at each car, and I'm starting off with a large velocity vector, and I have starting to slow down because I'm getting closer and closer. The dots are getting closer and closer, and the time intervals are the same. And therefore, I must have an acceleration. But what is the acceleration? It is in the negative direction. My velocity is in the positive direction. So sure enough, I'm slowing down because I have opposite signs between my velocity and acceleration. Okay, hopefully that makes sense. So now let's take a look at this picture here. I have a figure below is a motion diagram of an air puck moving to the right on a horizontal surface. The images sketched are separated by equal time intervals, and the first and last image show the puck at rest. So select which color graph, which I guess is on the next page. That's not easy to see. Which color graph represents the puck's position, velocity, and acceleration as a function of time. So the first thing I'm going to do before I even get to that, I'm actually going to go in here and draw some velocity. Let's do red for velocity. Velocity is going to be a red. And let's do acceleration is going to be purple, like what they did before up top. All right, so we started at rest, they told me. And so I'm moving to the right. I have a little velocity vector. And remember, these dots are at equal time intervals, right? But the distance away is starting to get bigger. So my velocity is starting to increase. My velocity is now increased. Now it looks to me like I'm having some constant velocity. And then I notice that all of a sudden my velocity gets smaller and smaller and smaller, and I have no velocity, okay? So what's happening to acceleration? Well, my acceleration had to be there because eventually, well, I started to speed up, but then I noticed that the distance between the dots is the same. So is the velocity changing? No, so acceleration is gone. Then I started to slow down and acceleration had to move to the left. Okay, now we have to find position versus time curves that match that puck, okay? So take a look at, let's actually start with what I consider the easiest, which is velocity versus time, and then go to acceleration, and then go to position versus time. Because sometimes the position versus time is more challenging. That's my opinion. So let's start with velocity first. And I know that the velocity started off at 0. So notice that all of the curves start at a velocity of 0. So that's fantastic. So then what's happening? The velocity is increasing and then becomes constant. So notice that the red curve is increasing, the green curve is increasing and then becomes constant. So those two are possibilities. And then it starts to decrease and eventually goes to 0. This blue line I can eliminate because at no point in time did the blue graph actually flatten off and become constant. So now I know that this is gone. So I cannot have the blue curve. So I like to do things by process of elimination. And then if you notice, did at any point in time, did the velocity of the car become negative? And so again, I'm looking at velocity versus time. I never became negative, so therefore I cannot be green. So this would be the red. This is the correct answer. So red would be the correct answer in this one. This is good. Okay, now let's go to acceleration. At one point I had a positive acceleration, then I had 0 acceleration, and then I had a negative acceleration. And you can see these step changes on green, and that would be the correct curve that is associated with that. Now I'm going to go back and see what's happening to my position versus time curve. Notice that in the beginning, the velocity is changing, and so I have to have some type of curve, and so the blue line is curving. It's kind of hard to see. This is not the greatest example. And then right about here, it flattens off until about there, and then it starts to curve down. So the blue line is correct for the position versus time curve for that particular motion diagram. All right, moving on. So I'm going to actually give you the opportunity to pause your video and give me a description of what you're seeing in these motion graphs. Assume the object is moving from left to right and that right is positive. Okay, so here are my answers. This is how I would describe the first motion diagram. If you notice that the dots have the same distance between them and the time intervals are the same, therefore it is moving to the right at a constant speed. So I could actually come in and put my velocity vectors on top and they would have the same length the entire time, and I would not have an acceleration vector on that in that situation. In this next, so it is moving to the right at a constant speed, acceleration is 0. Now this purple one, I would have again, a constant velocity vector because the distance between the dots are the same, but the velocity vector would be larger because the distance between them in that same time interval is larger. So it's to the right at a larger speed compared to the black dot. Again, the acceleration is equal to 0. This green one actually is got a small velocity vector, then it gets larger, and then it's just continuing to increase. And because I do have a change in velocity, I have an acceleration vector. And so it is moving to the right with increasing speed. Velocity, you notice, is positive, acceleration is positive. And the last one, I have a velocity vector that starts off, let's make it a little more obvious, with some large velocity vector, and then the velocity vector starts to get smaller and smaller. And so I have acceleration, I'm going to assume that it starts here, and the acceleration is in the opposite direction because I am moving to the right with a decreasing speed. So I have a positive velocity and a negative acceleration. Okay, hope that makes sense. Here's another question for you. In the following motion diagram, when do the black and green dots have the same position? At what time do they have the same position? Okay, so once again, don't forget these are at successive time intervals. So I have, we'll call that time 0. This is 1 second. This is 2 seconds. This is 3 seconds. This is 4 seconds. Let's see if I can write an S. 4 seconds, 5 seconds, 7 seconds. So at what point does the two objects that are displayed here in this motion diagram have the same position? Well, right away, I find that 0 seconds, they have the same position. What about 3 seconds, they have the same position? Some of you might have said 7 seconds, but if you notice, if I were to draw a straight line, the green dot is actually slightly to the right of the black dot, therefore it is not actually at the same position. So that is when they have the same position. Okay, when do they have the same speed? Well, what is speed? It's the distance over time, right? So when does the distance between the two dots, a set of dots between the two, black and green, have the same length? And so what you can see here is this distance looks very close, in fact it is, to the distances above. You just have to use this is just, again, an exercise here. So we know that between 1 and 2 seconds, the speed is the same. Okay, I've never really seen that on an AP exam, but I'm just trying to help you solidify your understanding of what a motion diagram actually tells us. That concludes my lecture on motion diagrams.